Okay, now let's look at minimax again, but now this time extended with a heuristic function. And let me start with motivating why we actually want to have a heuristic function involved here. Well, it's because we live in a world of imperfect decisions. In reality, we don't have the time to search through the complete game tree. And this basically means we can't reach the terminal states. Since the complexity of minimax is exponential in to b to the power of m, we basically, in reality, for all the games that are actually interesting, that warrant an AI solution, there is no chance we'll be able to reach the end states, right? This basically means that we have to make time-bounded decisions, and since we are time-bounded, this means the decision is going to be imperfect. And this is where heuristic comes into play. The idea then is that, instead of going all the way down to the terminal states, we'll have to cut off. And the search is going to be cut off at a certain level. Let's denote the level with D. And at that level, we'll have to make an estimate of the payoff function. Now, these states will not be the terminal states. Hopefully, they are closer to the terminal states, right, than where we started off from. But still, these are not the terminal states, and we'll have to make an estimate. And the estimate of the payoff function is going to be made with the heuristic function. So the heuristic function here, same as what we had 2 weeks ago, the heuristic function is going to estimate something, but the difference here, it's not an estimate of a distance from a state to the goal state, rather it's an estimate of the payoff that I as a max player can expect to get if I continue playing the optimal strategy from that particular state. And therefore, the heuristic function, unlike what we had a week ago, the heuristic function can be positive or negative, right? Positive means I can expect to get a positive payoff, which basically means I can expect to win, whereas a negative value would mean I can expect to lose, and that's the penalty that I'll get. So the value of the heuristic function, again, we'll denote it with h of s, is going to be an estimate of the expected utility of state S for the player max. It's always going to be from the perspective of the max player. Now, to give you an example of a heuristic function, think of chess. And when you look at the chess board, even if you're not a chess player and maybe you're looking over someone's shoulder who's playing chess, I guess you would be able to tell most of the time if that particular board configuration is good or bad for the first or the other player, right? Simply maybe by just looking at the pieces that are still on the chessboard, right? And one way to formalize this is to come up with a heuristic function that sums the so-called material values of the chess pieces. And by material values, I simply mean that not every chess piece has the same value, right? And depending on these material values that you can have predefined, you can then basically come up with a function defined as a weighted linear combination of these number of different chess pieces. So, for example, x1 can be a certain chess piece type, and then W1 is going to be the weight that I think should be associated. That's the material value of that chess piece type. And then similarly for other chess piece types. I might extend this, and I might look into more sophisticated ways of defining the value of a board, the merit of the board for the max player, the expected utility, maybe in terms of how open the configuration is, or how prone to attack of the opponent, and so forth. So basically, you can build a lot of expert chess knowledge into the HS function, and that's really where the creative part of game playing in AI comes to play, right? In the defining of the H function, because when you think of this, the min-max strategy and algorithm is well known, and everybody's gonna use it. So it's not going to be the the important difference here between the game playing algorithms. It's not going to be what's going to decide the game. The difference, the essential difference, will be in the definition of heuristic functions. Okay, obviously, not only in the definition of heuristic function, there's also implementation details that are important. How efficient your search algorithm is going to be, and how deep can you go in a certain limited amount of time. But I'd say, by and large, the most important point here, obviously, is going to be the heuristic function, and how creative on one hand, and also how efficient you can implement this function. Another thing to note is that the players typically will use different heuristic functions. And this is to say that I will be implementing my max algorithm, and my opponent, maybe also an algorithm, will be implementing the same minimax strategy, but our heuristic functions are not going to be the same. And that's exactly why, from my perspective, the other player appears to be unpredictable. Since the player is not using the heuristic I'm using. I'm using my heuristic to choose my moves, and I'm also using my heuristic to predict the moves of the opponent, but the opponent is using a different, maybe slightly different, or entirely different heuristics. And therefore, from my perspective, the guy seems to be unpredictable, whereas in reality, the opponent is actually using the same strategy and very predictable. It's just that the heuristics of this other player is something that's unknown to me. Okay. Now let's extend the minimax algorithm with the heuristic functions, and the modification here is actually minimal. The only thing I'm going to do here, I'm going to add a d as a parameter to both of my mutual recursive functions. D is the maximum depth. That's the depth that I'm ready to go to, and once I reach this depth, I'll cut off the search and I'll make a call to a heuristic function. The idea is that as I progress in my search, as I go one level deeper, I will decrement d by 1, right? And then once d is equal to 0, this essentially signals to me that I've reached the depth limit. And I'm including an additional test here. Besides the text for the terminal node, I'm including one additional test here to test if the depth is equal to 0. And if this is the case, then I'm returning the heuristic value of that particular state. And I'm doing the same here for the min value function. So notice that I now have two basic cases, two exit conditions from both of these functions. The first one is when I reach the terminal states, and it's rarely gonna happen at the very end, when I get closer to the end. And more often I'm going to hit the depth limit here, and I'll return HS, which is essentially an estimate of the utility of S. Okay. Now time for some practice here. First, let's start with just recalling the basic minimax computation. And we have here a game tree, simple one, defined by certain transitions here. The successor function of A are the states B, C, D. So there's a state A here, and there is B, C, and D here as possible moves for the max node. Actually, min node is going to be first, as we're going to see. But yeah, let me do the tree first. Then the successor of B is E and F, and the successor of C is G and H, and that successor of D is I and J. Okay. And next we have the heuristic values of the leaves. Let me change the color here to make it more colorful. H of E is -1, of F is 3, H of G is 2, H of H is 4, 5, 1. Okay, and now the question here is, what is the minimax value of a node of the root node A if it's the min's turn? Okay, so now I know that, this is a min node here, and then this has to be a max node, and this has to be min node again, though actually this last level here is not really important since it's the terminal states. And now applying the min-max computation, I know that the max node is gonna compute the maximum of these two guys, which is 3. And then the maximum of these two is 4, and the maximum of these two is 5. And I know that the A node, being a min node, is going to compute the minimum of these three values here, 3, 4, and 5, and the minimum is 3, right? So the min value, the minimax value of the A node is 3, and this here is the correct answer. Okay, I hope this made sense. Now let's look at a more interesting situation here where we actually have heuristics, right? And now we are having here one heuristics, and we assume that this heuristics is used by both players. But what is interesting here is that the players search 2 levels deep. Now this is actually quite a realistic setup, since in reality you would have a certain horizon, the depth that you can afford to search in terms of the time that you have available. And as the game progresses and as you move down the game tree, then this horizon is essentially moving with you, right? So it's always 2 levels deep that you can search. So the max player here, this means can only see down to this level, whereas the next player will be able to see 1 level further. Okay. Now this makes the whole problem here a bit more interesting. So let's see, the question here is, what is the game state's end if each of the players search 2 levels deep? So the max is on the turn, that's the max node with an upper facing triangle, and the max node makes a call to a min node here, and the min node computes the minimum of 1 and -2, and the minimax value here is -2, the min of 3 and 2 is 2, and the min of 0 and 5 is, what is it, is 0. And now the max node chooses the maximum of these 3 values, which is 2, right? Okay, so now we know that, and notice again that the max player, is not really able to see beyond this level. Maybe the computation would have turned out different if the max player had been able to look 3 levels deep, but which is not the case in this problem here. Okay, so this basically means 2 is the max here. That's the minimax value of the root node, which signals to me that I'm going to make the middle move here. And the game changes to this state. Okay, now let's clean this to, yeah. Now we are here, right? Now it's the min's move. Min is also able to see 2 levels deep, right? So in this case, this means that the min player is seeing all the way down till here, and the min player essentially uses the same logic. The logic is -1 and 0, and it's you have to compute the max of these 2 values. It's 0, and the max of -2 and -1 is -1. You can disregard these heuristics values here, since you are now looking 1 level deeper and you are recomputing these, right? The min node is going to choose the smaller of these 2 values, which is, right, -1. So min is making this move, right? Previously we had this move, now we had this move, and we are here. And max now is going to make a move, and assuming that this is actually the end of the game, otherwise, max would be able to see further, but assuming that this is the end of the game, these are the terminal states, then, the only option available to max now, to maximize his win, is to make this move, and you'll end up with -1, which basically means he has lost the game, but, it's much better than -2, obviously. Okay. One important thing I'd like you to note here is that, again, this whole thing here was a computation done in the mind of the max player, this player here, right? So max was on the move, and then max made this one move, and then what max was doing, he was computing what moves the min player would actually be doing, right? And how do I know that this is the case? And when I say min is making a move, I was actually, maybe it was better to say max is thinking that min wouldn't be making the move, right? Since all of these things happen in the mind of the max player. And I can be sure of this since I'm using, these heuristics values of the max player. I don't know about the heuristics of the min player. In reality, the min player would have a different heuristics, right? And that's a more realistic setup then, right? So let's look at that setup where the values here are actually the heuristic values, the heuristic functions are different. So no, the question is the same. What is the game's end state? And let's again assume that each of the two players search 2 levels deep, but now they are using different heuristics. The first player is using the blue heuristics, the heuristics H1 with the values shown here in blue, whereas the other player is using the red heuristics, the values here indicated with red. Now to make things simpler, the thing is, when Max makes a move, and let's say, this is the move he makes, and then we are here, then it's the min player turn, and then from the perspective of the min player, he would also want to maximize the value, and we would need to switch the triangles and redraw the 3 each time anew. Now to simplify this, the idea is let's assume that this tree is drawn from the perspective of the max player, and therefore the heuristics of the other player will appear as negated here, right? Since the other player is trying to maximize his heuristic from the perspective of the max player, it appears to be as a negative value, right? Okay, this basically means that we can retain the semantics of these nodes. The max node is always going to be the node maximizing, the min node always going to be minimizing. But you have to keep in mind that these values shown in red, the heuristic values for the second player, are actually negated, and in reality the min player would have this as 2, this is 4, this is -1, this is 2, but we are negating this value to have the 3 drawn from the perspective of the max player. Okay, now with these conventions we can try to sort to solve this problem, and yeah, let's try to do this. Okay, so the max player is on the move, and he can see 2 levels deep, which basically means all the way down until here. Everything beneath it is not really observable to the max player here. So the max player is using his heuristics, which is the blue heuristics here, and doing the ordinary min-max computation, which basically means, okay, I know that it's min's player here, and the min's going to choose the lower of the 2 values, and it's going to be -2, and then the lower of these 2 values is going to be 2, and the lower of these 2 values is going to be 0. Okay, and since now it's my move as a max player, I'm trying to find the max value, and it's the 2 here, so I'll make the middle move here, right? Okay, so I'll be in this state. Okay, notice that the max player is not really able to see. He has no access to the red values here, because those are the heuristics values of the other player that are unknown to the max player. Okay, so the game has shifted to this state. Okay, so let's see what happens next. Let's change the color to reddish. Okay, here we are. And now it's the min's player turn, right? Okay, cool. Now the min player is actually trying to do the same thing, and now the min player is basically doing the same computation in his mind, but the min player is seeing the red values, but the red value is going to be negated for the min player. But since this tree has initially been drawn for the max player, let's go with this tree and just do the min here, right? Okay, cool. So the min player is able to see 2 levels deep, and this basically means the min player is thinking like, okay, this guy's trying to maximize his win, and he is choosing between -3 and -2. Now, this being the min player is using the red statistics H2 here. And the min player is now thinking, okay, the max player is going to choose the larger of the two, which is -2. Now, this incidentally happened to be the same value as what he had before here, which need not be the case. Okay, and then in this state, the min player is thinking about the max player who will be trying to maximize his values 1 and -1, and it's going to be 1, right? So you can cancel this one, it's going to be 1. Okay, and now the min player is basically saying, okay, it's either -2 or 1 for me, and I'm going for the lower value, which means I'm making the left move here, and the game changes to this state. Okay, and now it's again the blue player's turn. The game's here, and the blue player now again starts the min-max computation, and let's assume that these are the end states here. There is nothing beneath this level, and in this particular game state there is not much to do, not many options for the max player. The max player trying to maximize his win, looking at -1 and 0 essentially. The max player is gonna choose 0. Okay, I think for some, I guess I made a mistake here somewhere, because the official solution should have been slightly different. So maybe let's go back a couple of steps and just do a quick recalculation here. So the max player is seeing 1 and -2, so it's 1. Sorry, the min value here is -2. It's 2. And it's 0, so the max player makes this move, so this was correct. Okay, cool. Let's look at the min player again. If we are here, the min player is computing the max of the red values, -3 and -2, so it's -2, and the max of 1 and -4 is 1, and then chooses the minimum of these values, which is -2, right? Here, -2. Okay, so the game's here, and then great, and then it's again Max's turn from here, and Max chooses the maximum value, which is 0. Okay, so I guess, unless I'm mistaken, this should be the optimal strategy, right? Ending with the value of 0 for player, the blue player. Okay, so keep in mind that this is probably the most realistic setup that we can come up with, where the two players search a certain amount of levels in advance. It need not be the same number of levels. In this case, it was the same. It was 2 for both. And there is different heuristics that I use. And then you have to be consistent when you compute the min-max value for the max player. You use only his heuristics, and only until the level that the player is seeing. And then when you switch to the other player, then you switch to the other heuristics, but otherwise you just follow the same logic of max and min. Okay, I hope that made sense. And next we'll talk about how to make the search a bit more efficient using alpha-beta pruning.